So I'd like to have the opportunity to share this bit of work that I do with you. I should say, I think you probably got this feeling from the abstract, that this is not as removed from wireless as you might think. As we speak, it turns out that, well, you'll see some things in here that clearly have wireless applications. And it turns out that various techniques we play around with show up in other things that I like to do. For example, Mike Buer and I right now are playing around with an idea that came out of radio astronomy work for geolocation. So it's, there's all kinds of weird applications from this. But this is not the reason to be interested. The reason for being interested in radio astronomy is it's just cool and lets you get your full engineering, electrical engineering geek on, which is kind of what I like. So I want to talk about fast radio bursts, one of these things I play around with. How wideband real-time signal processing is solving one of the greatest problems in modern astrophysics. And I'll explain those two pictures there as we go along. So a quick outline. First, an engineer-friendly crash course in astrophysical radio pulses. I presume that most of you are newbies from the radio astronomy perspective, but that's okay. It's pretty simple to understand. So a bit of signal processing theory, which you will not even perceive as theory. It's just a method. Fast radio bursts, the kind of mystery I want to talk about. Then these two instruments. One is called GBTrans. It's an existing project between us here at Virginia Tech, West Virginia University, and NRAO for looking for these things, FRBs. And that's also a subtext in there is the implementation, so the wideband high-speed signal processing thing. And then LASA, which is this new instrument that we propose to do this, proposal going in Monday, as a matter of fact, to build a new large array for doing this. So I'll say a little bit about this. Some acknowledgements. West Virginia University, my collaborator most directly on this stuff is Duncan Lorimer. He's an astrophysicist at West Virginia University. NRAO Green Bank, who tolerates all this mad scientist stuff. So they let us get in and use their instruments in ways that they had never intended, and their real estate in ways that they had never intended, and provide, contribute technically as well. And then countless people whose ideas I have co-opted without attribution, as usual. So I'm going to start off with something completely different, Pulsar Basics. What is a pulsar? A pulsar is an end product of a star's life. So stars can die in various ways. One way they die is they explode, and then a fraction of the material collapses onto itself and forms this thing called a neutron star. Neutron stars are spectacularly dense things. So you've probably heard this from some kind of popular science show or whatever. And what we get is something like this when the smoke clears. It's an ultra-dense thing. It inherits magnetic fields from its progenitor. Actually, the magnetic fields are highly intensified. And it still spins. It inherits its angular momentum from its progenitor, the star. So it's spinning. And the spinning magnetic fields give rise to electromagnetic radiation, which in this case is collimated along the axis of these through which the magnetic fields flow through the neutron star. So there's rotation in one direction, and then there's a radiation beam that's popping out in both directions, and the radiation beam then is spinning around like a cone. And we refer to this as the lighthouse effect, and this whole model is the lighthouse model. So what happens is if the Earth is in the radiation beam, every time the beam comes around, you see a blip. Right? If the Earth is not in the radiation beam, you see nothing. So all the pulsars that we ever see are just the fraction of pulsars for which the radiation beam lines up. So here's a picture of what we see, or how we perceive pulsars. This is actually LWA1 data. LWA1 is one of my instruments. And this is a time frequency depiction. So all of us, I think, know about dynamic spectra and those kinds of things. This is frequency, in this case from 67 megahertz to 85 megahertz. And that's 13 seconds along the x-axis. And what we see as that pulse comes around is something like this. So this is real pulsar data. This is what pulsar pulses look like. I'm highlighting in one version just so you can see more clearly what's going on there. What you'd expect at first glance might be just a simple pulse, right? But we don't see that. And the reason is because space is not empty. Space has free electrons in it. And whenever you have free electrons and signals propagating through media consisting of free electrons, as space at BT people will know, because the ionosphere is the same way, you get dispersion. What dispersion means is high frequencies arrive first, low frequencies arrive last. So even though space is utterly empty, except for this very low density of electrons, we still get significant dispersion. And at these frequencies, you can see it very clearly. You see the high frequencies arrive early, but that pulse gets stretched out, so you see a chirp instead of a pulse. So if you just try to detect this and you're not clever, you just do total power and you see nothing because all the pulses overlap. All right? So what you have to do is a process known as dedispersion. Dedispersion, I'll explain in just a moment, is the undispersing of this. So you get regular pulses and you can do regular traditional impulsive pulse matched filtering. There's two things you get from this right away. The curve, the discrete at which it's dispersed, tells you the distance to the pulsar. So if it's further away, you go through a higher electron density, column density, you get more dispersion. If it's very close, you get relatively less dispersion. You also get this thing called broadening, which is due to inhomogeneity in the pulse and electron density along the path. Not really a topic here, just have to come along with that slide. So here's incoherent dedispersion, the theory I alluded to. If you want to detect these, the wrong thing to do is simply to add up all the frequency columns to get a time series like this, because you just get these rather indescript little humps, right, which are the smeared out dispersed pulses. So what you do instead is you take, and this is called incoherent dedispersion, by the way, you take the time frequency incoherent spectra, you advance the, or you delay the highest frequencies by the right amount, and the lowest frequencies by relatively less amounts, so that you've effectively removed the dispersion. Now you add it up, you get nice big pulses, which presumably are what came from the source. So perfect dedispersion gives you something exactly what was issued from the source, and to the extent that you screw that up, you get something that's smeared out. So this is not the optimal thing to do. I'll do a little bit more signal processing. The optimal thing to, of course, do is to coherently remove the dedispersion. So there is a coherent dedispersion process that I could talk about, which is utterly intractable for anything that I'm going to talk about in this talk. Generally only works if you know exactly what you're looking for, and then it's computationally very difficult to do. Incoherent dedispersion is relatively simple, which is the reason we like it for searches, because all you have to do is move these pixels around. Because this is really all this is you've got these incoherent, these little pixels, and all you're doing is moving the time frequency pixels around to do dedispersion. And that's bad enough, but we can pull that off. So this has low computational, just this much has low computational burden if you already know the dispersion measure, which is the case for known pulsars. So there are people out there who just spend their time looking at known pulsars, and that's great. But if you don't know anything about dispersion measure, you're looking for something new, it's a nightmare. And the reason is because you have to keep repeating this process for all the possible DMs that you think might apply. And then the one that gives you, of course, the biggest pulses is the one that you assume to be the right one. So that's rather computationally intensive, but that's what you have to do for pulsar searches, and this is what you have to do for single pulse searches like what I'm about to talk about. Typically, somewhere between hundreds and thousands of these iterations that you have to do to get it right. Okay, so there's pulsars. Now we go to single pulses. So it turns out some pulsars just produce the regular pulsar emission, the lighthouse emission, but then every once in a while, for reasons which nobody knows, they produce spectacularly bright versions. So for example, this is one of my favorite pulsars here, known as the Crab pulsar, because it's in the Crab Nebula. For some reason, nobody understands, it's got a period of 33 milliseconds, but every couple seconds or once an hour or whatever, it'll produce a spectacularly bright pulse. So in this data, you would never be able to see the periodic emission of the Crab pulsar because all those pulses would just be overlapped. But what happens is every once in a while we get one of these spectacularly bright ones and we have no idea why. Right? So this has been a topic of my work for almost a decade now. And this is just one example. So here's two that just happen to be relatively close together in time. But again, these pulses are going off every 33 milliseconds. So this is a spectacularly bright and very anomalous thing. So many of us have been curious about this. We still have no idea why they happen. We've got a bunch of theories which are all unverifiable at the moment. Something that came up is, well, you know, if pulsars do this and we don't know why, maybe there's other things that produce single pulses. See, it turns out single pulses are pretty hard to find because they're rare. And you got to know which DM to look for. So that's a lot of work to look for a particular, to do the search. So myself, as well as a lot of other people, but I'll just describe my own, this is your futile efforts to do this, have been looking for other sources of single pulses just to see if there are some. So the story goes like this. There's a lot of enthusiasm around 2000 and 2003, right around the time I came here, as a matter of fact, about the possibility of finding exotic objects other than pulsars using this mechanism. So anything that involves charged particles being pushed through magnetic fields will produce a pulse. And there's lots of things that can do that. One of the things that I'm interested in, I will spare you the theory about this, is exploding primordial black holes. So these are things that we believe exist, and the only way we can ever detect them is if we see their signal pulse emission. So we're very eager to find those. And there are other things. I'll mention a list of things that could possibly produce this emission besides pulsars. So we're interested in going out and finding instances of this. In around 2000, 2003, the conventional wisdom was the best place to look for these was below 100 megahertz. There's a whole bunch of theory associated with that pointed to VHF frequencies as being the place to go. So in fact, my very first funded research project at Virginia Tech was this thing called ADA, the 8-meter wavelength transient array of 12 dipoles with a big FPGA backend, looked at the whole sky, continuously churned on the sky and looked for these things, doing incoherent dedispersion all the time for the whole sky. Found absolutely nothing new except for what we already knew would be there, so pulsar giant pulses. So that's good news because we knew it was working, because we were seeing pulsar giant pulses, but we didn't see anything else. So that was disappointing, dismantled in 2009. One possible reason that could have happened was, well, maybe they're just not big enough. Maybe we're just not digging deep enough. We don't have a big enough instrument. So I became involved in this project called the Long Wavelength Array, which some of you probably heard of. That was originally funded by the Navy because these frequencies have a lot to do with ionospheric propagation mechanisms. Turns out this has applications there. We've got the Navy to pay for the construction, and then NSF to pay for the operation. This particular instrument, 40 times more sensitive, 10 times as many antennas, and 4 times the bandwidth, so 40 times more sensitive. Still found nothing new, but was great for other reasons. So we built this thing. It was very expensive. We looked. We didn't find what we were hoping for. But it turns out it's a great general purpose instrument at these frequencies, so no disappointment there, except for me, because my reason for going into that was to find these things. Turns out other people are still doing this. So these 2 big major instrumentation projects, instruments now operating, LOFAR and MWA, operating at similar frequencies, still looking, so I don't feel so bad, because they're not finding anything either. Well, then suddenly there was this thing. This thing we call the Lorimer Burst, named after my collaborator, by the way. So he's a pulsar guy. He was doing what pulsar guys often do, which is just search for new pulsars, right? So he's running this search at Parkes, which is New South Wales, Australia, using this instrument, the Parkes 64-meter instrument, and collected data 2001, and as typical, didn't get analyzed until about 5 or 6 years later. When a student analyzed this, pulled out this plot and said, hey, teacher, what is this thing? Advisor, what is this? And of course, Duncan knew exactly what it was. It looks like an FRB, or looks like a signal pulse, the kind of which many of us were interested in. So this is the seminal example of a real unknown source generating a single burst. No idea what this is. In fact, there was a lot of, he got a science paper on this, which is pretty amazing, since he couldn't say what the source was. A lot of enthusiasm about this originally. People ran out and started observing like crazy to try to find follow-up examples of these. Then there was skepticism. One problem was nobody else could find them. Parkes kept finding them. So this is a little bit suspicious. Is it that we can only detect this emission in Australia? That doesn't seem like a reasonable assumption. Then there was more problems, these things called peritons. I don't know if anybody here knows what a periton is. Periton is a mythical creature. It's a winged elk, but the winged elk has cast the shadow of a human. So the shadow looks like a different animal than the thing that cast the shadow. So it's an apt analogy of what happens here. Periton is RFI, interference, which just happens to have a signature that looks like that. So they had a rather unfortunate incident at Parkes where they discovered that the microwave oven in the cafeteria at Parkes, if you opened the door when it was running, produced a dispersed pulse. Now that wasn't this pulse, but it turned out that all these other pulses that they were finding were that thing. So Duncan went through a rather unfortunate period where people kind of casting dispersion on this possibility, and then the smoke kind of cleared and realized, no, that one's real, and then there's other class of things that we have to be careful of that aren't real. So, brings us to the present. This is all the fast radio bursts, which is what we call these things, today. Every one of these things is a highly dispersed pulse. Highly dispersed, again, meaning it must be very distant, right? They're relatively bright, but they're hard to find because they seem to happen relatively rarely. So these are it. There's a total of 11 right there. I'm told number 12 is about to be published in Nature. So I thought it was going to be this week, but I guess it's going to be next week. So there's going to be one more added. But you can see kind of the history of what's going on here. A whole bunch of measurements made in 2001, and then 2011, when people start realizing that they might be real. And you can see the elapsed time between the measurement and the reference year, the year for the published reference, getting smaller and smaller as people get more excited about this. Parkes was the only place I could find them for a long time. I'll tell you why that was in a moment. Then Arecibo found one, big sigh of relief. So now we're just finding them somewhere else. And then, of course, what you really have to do to detect these reliably is do the real-time processing. Parkes put in a real-time processing system in 2013, got their first real-time detection in 2014. That's the bottom panel. So what we're talking about doing is really extending this list by orders of magnitude. They're probably extragalactic. So I think we all know that we live in a galaxy, a collection of stars, which is distinct from other collections of stars. There's a picture of what our galaxy might look like. We would be over here somewhere. We kind of live in the suburbs of our local galaxy. And what I'm about to show you is why we know, or why we're pretty sure that these are extragalactic. These lie outside our galaxy. And it goes like this. You can make a plot of dispersion measure, which is the total amount of measure, a single number that describes the amount of dispersion. So this is analogous to distance across the bottom. Then you can also make a plot of that dispersion measure divided by the maximum dispersion measure you could anticipate by going through the galaxy. And see, the reason we know that is because we know something about how electrons are distributed in the galaxy. So for any line of sight going out of the galaxy, we can come up with a guess of what the maximum dispersion measure would be. So if we divide the actual dispersion measure by this maximum dispersion measure that we would expect to see along that line of sight, then if it's below that line, it's probably galactic. If it's above that line, it's probably outside the galaxy. So if you take every pulsar ever found and you plot it, sure enough, they're almost all galactic, right? Because they all lie below that line. For pulsars which we know about that are galactic, extragalactic, lie in other galaxies, those are those boxes. And sure enough, they lie above the line. And then the diamonds are all the FRB detections, all 11 of them. Well, this time there were 8, so it's only 8. But there'd be 3 more up there, and they'd also be above the line. And they're all above the line, so we are pretty sure they're extragalactic. It's not completely compelling, because you can come up with, and people do, all kinds of weird theories about how you can generate very high dispersion measures, like in solar atmospheres and things like this. So it's not 100% certain, but that's about as good as it gets for evidence. So we're pretty sure about that. So what do we know? We know they're probably extragalactic. If they're extragalactic, then they must be extraordinarily bright. The way we measure how bright these things are is in terms of raw energy, because they're impulses, right? So impulse is a certain amount of power over a certain amount of time. So to describe it in terms of the total energy, these things have energies on the order of, implied energies anyways, on the order of 10 to the 30 to 10 to the 33 joules. I will tell you that when these things go off, they must be the brightest things in the universe. That's how bright they are. There's nothing brighter in terms of intrinsic temperature. We know the instruments very well. We know how long they've been looking. We know over what sections of the sky they've been looking. And we know how many they've detected. So we can infer from this, just simple statistics. Any statistics is simple, but simple statistics, roughly how many per day occur. Right now, the best guess number is about 4,000 per sky per day. So that means if I were able to somehow be sensitive to every FRB that goes off in my, visible from Blacksburg, there should be 4,000 per day, right? So you mean, why aren't we detecting more? Well, because the telescopes that are detecting these have beam widths which are arc minutes wide. So if you take my Blacksburg analogy, just imagine now trying to see those things by looking through a soda straw. And now 4,000 per day could be going off, and you'd be lucky to see one, because the soda straw would always be looking at some wrong part of the sky. Important to remember that analogy, becomes important later. Another problem is localization is very poor. Even though arc minutes for a telescope beam sounds wide, or sounds small, and it's a big dish, so it's a narrow beam. The beam is arc minutes wide. That means fractions of a degree wide. Well, the problem is that there are lots of things astrophysically that can occur within a few arc minutes. So there are many galaxies, for example, every few arc minutes in the sky. So we can't really tell with this kind of localization whether they're always associated with galaxies or whether they're not. And that's important, because if we could always determine that they were always associated with a galaxy, then we'd know that they were star-like mechanisms, or mechanisms associated with galactic mechanisms. If we found instead that they were utterly homogeneous and we could not attribute everyone to a galaxy, that would imply they were cosmological, that there's something more profound, maybe something that's happening in the early universe. So utterly, this is extremely important to be able to do this localization much better than we can do it now. Not yet seen outside of L-band, but that's because nobody looks outside of L-band. So all the observations that have been done so far are around 1.4 gigahertz, plus or minus 200 megahertz. They typically done with about 400 megahertz bandwidth. 400 megahertz of bandwidth only at parks at Arecibo, because they're the only people who look, right? I'll tell you, the new one looks like it might be 800 megahertz at Green Bank, but we'll see next week when the Nature paper comes out. Not surprising, again, because those are the only people looking, right? But there's some news expected on this very soon. So what do we think they are? Well, I categorize, well, first of all, the box on the right applies. Nobody knows, which means we should be working on this. But there's three classes of possibilities here. I list the exciting possibilities, the really exciting possibilities, and then the less exciting possibilities, but hard to rule out. Exciting possibilities are things like, and I realize this is not a fair term to lay on an audience and then walk away from, but magnetar hyperflares. Magnetars are special pulsars. They're extremely exotic, but it turns out that if you, we know that they exist, and we think they can produce these hyperflares, but we've never been able to confirm that. These might be them, but we're not sure. Coalescing neutron star binaries. A certain very, very rare fraction of systems end up with two neutron stars orbiting each other. And as they orbit each other, they lose energy and they in-spiral. At some moment, they contact. When they contact, all hell breaks loose, and there's a big impulse. We expect that to be a possible source. Exotic supernova mechanisms. Then the really exciting possibilities. Evaporating primordial black holes, my personal favorite. Happy to share with you what that's going on with that if you'd like, but that takes a while to discuss. Cusping cosmic strings, same issue. Astrophysical and technological. So this is my way of saying extraterrestrial intelligence. I never like to write that on a slide, because I find as soon as you say that, everybody goes nuts. And it's not that. It's just that you can't discount the possibility that maybe there's some technology out there somewhere in the universe that produces these things, and people have taken it seriously. These two guys are eminent radio astronomers. I don't know, maybe. Less exciting but hard to rule out, giant pulses from extragalactic pulsars, flare stars, atmospheric peritons, things in our own atmosphere that might be able to generate enough dispersion to fake us out. Then anthropogenic peritons, which is a fancy way of saying interference, like microwave ovens. So what needs to be done? Well, we need to find orders of magnitude more, like thousands. Thousands would be about the right number to find. Then we can start sorting it out. Better localization. So right now we do arc minutes. Arc seconds is what it takes. To get arc seconds localization, you need kilometers of aperture. So you can't really build telescopes, single metal telescopes that are kilometers wide, but you can't build arrays that are that wide. So we need arrays that have baselines up to kilometers. You need to find more bright FRBs, bright enough so that we can figure out very precisely their scattering profiles and their polarization characteristics. They have to be linearly polarized, or none of these theories really work. So we're desperate to kind of figure out right now whether they're linear or circular or whether they're just random. That would tell us a lot. And then eventually we associate with other wavelengths. So now let me tell you why finding FRBs is hard, and this leads to the technical part. Here's my explanation of why we don't see a lot of FRBs, or why this was a surprise when it came about. It also tells us how to design experiments that search. So on the horizontal axis, we have signal-to-noise ratio. Right? Big instruments can get big signal-noise ratios for a given burst. On the vertical axis, we have detection rate, number of these detected per day for the indicated signal-to-noise ratio. Ironically, a big instrument hurts you here. In fact, here's the picture. Something big like Arecibo will generate high signal-noise ratio, but the beam is so narrow that the detection rate's tiny. Right? On the other hand, if you take just like a small dish, right? Well, there the signal-noise ratios are very, very low, but the beam is gigantic. It's like 7 degrees wide at L-band. Well, there you might be detecting 2 or 3 a day at the event rate that we currently expect is the right one. So every other possibility tends to fall in this line. Now, at the same time, you can identify the range for productive searching here. What you'd like to be able to do is achieve consistently a certain signal-noise ratio, which I've arbitrarily shown as 6 here, and then a certain detection rate, right? So maybe 1 every 10 days or so would be reasonable, right? So if you want to detect one at least every 10 days with a signal-noise ratio of at least 6, you need to be that upper right-hand corner where I've labeled productive searching. And then you look at the possible instruments that we have, and there's how they're stretched out. So we have small dishes, which of course are useless because they have not sufficient aperture. Big dishes, which turn out to be useless, ironically, because their field of view is too small. So, on the other hand, we're getting close to the quarter there. There is a class of instruments which are about the right size. So if you plot all these instruments, and then you plot how they perform for the 2 classes of FRBs we've already found. I didn't say this, but it turns out there's one that's very bright compared to the others, and then the rest of them are a little bit dimmer. But and those are the red and blue lines. And if you show how those how different instruments perform with respect to those 2 classes of FRBs, this is what you get. So there's the small dishes in the upper left-hand corner. Here, about 2.3 meters is a small TVRO dish. On the bottom right is Arecibo Observatory. AO is Arecibo, biggest filled aperture in the world. Turns out we clipped the corner for dishes that are somewhere between 20 and 40 meters wide, which says if you want to do this right, what you should really do is use dishes or instruments of some kind that have apertures on the order of 20 to 40 meters, because they give you about the right trade-off between this event rate and signal-noise ratio to be competitive. All right? Then you ask the question, why is Parkes finding these? Well, one answer, of course, is because they're looking. Right? You have to look to find, and not everybody was looking. But one of the reasons they're successful at it is because Parkes is a 64-meter dish. Right? So it's a little bit too big from our perspective. But it turns out that they have a feed system that has 13 simultaneous beams at once. So what they do is they have a feed system where with 13 horns, and each of the horns are displaced slightly from the axis of the dish, which gives them 13 looks at the sky simultaneously. So from the perspective of this search, it looks like 13 64-meter dishes all going at it at once. So they get the signal-noise ratio of a 64-meter dish, but then it's like they're using 13 more of these dishes to cover more of the sky. So that jumps these numbers up and puts them in the box of productive searching. So that's a pretty good explanation, I think, of why they are able to detect them at such a high rate compared to other people. Because you'll notice Arecibo, for example, is down here. They too have a multi-beam system, but it's only 7 beams. So they start off disadvantaged because they're further down to the bottom and right, and they can't come up as far because they only have 7 as opposed to 13 beams. But again, they've detected one, so there you go. Well, so this is where I come into the picture. We spent a lot of time thinking about how we could more productively do this kind of thing. And once we realized what was going on here, we started looking around the world for dishes that would be suitable. It turns out right up the road here, 3 hours drive up into rural West Virginia, where there is no cell phone service, no FM radio, none of that stuff. This dish exists. This is not the Green Bank telescope, by the way. The Green Bank telescope is a gigantic 100-meter dish, which is utterly unsuited for this. This dish is a tiny little dish that kind of sits off on the side of the Green Bank campus. It's a mere 20 meters wide, But it turns out 20 meters is about the right place to be. It puts you in the right, at least in the neighborhood of productive detection, productive searching. So that's where we've gone. This is the instrument that we've used, that we've set up to do this. So this instrument, like all radio telescopes, and like all telecommunications receive side anyway, big dishes work. There's an RF section. We grab 1300 to 1800 megahertz, a big chunk of L-band, complete with all the radars and all the satellite telephones and all the junk that, all the productive wireless communications that goes on. I have to remember which audience I'm talking to at any given time.
That's fine, Steve.
By the way, I'll take money from anybody. It doesn't, I just love to do the technology. So we receive this stuff, we put it on fiber. We run fiber from the dish here, a couple kilometers back to a lab where all our equipment sits. The first thing that shows up in this thing, it's labeled Roach 1, is a spectrometer. Spectrometer is astronomer talk for something that produces dynamic spectrum. So what we're doing there is we're digitizing it at 1 gigasample per second, 8 bits. We're using a big Vertex 5 FPGA, then to produce dynamic spectra. In fact, I should show this picture. That's what the Roach looks like. By the way, Roach is an acronym. It stands for Reconfigurable Open Architecture Common Hardware, Computing Hardware, something like that. It is to radio astronomy what the USRP is to engineering research. Right? So lots of us use these things, these big FPGA engines under the Roach label. But what they fundamentally are is just Vertex 5 FPGAs with standard connections and some yellow blocks that have already been figured out and are relatively easy to use. In the same way that GNU Radio is easy to use. Right? So so we've got a Roach 1. What this does, it samples at 1 gigasample per second times 2 polarizations. We do a 1K FFT. We're looking for power, so we take I squared plus Q squared. We accumulate 32 of those. That gives us a time frequency resolution of 131 microseconds by 244 kilohertz. So there is our fundamental resolution element, right? So that's the thing we get to slide around in these time frequency diagrams to do the dispersion. From that, we get about 400 megahertz bandwidth usable, and it's continuous in time and frequency. So this thing is spilling out 400 megahertz of bandwidth already tiled into these time frequency elements, and that's incredibly useful. We pump that across the internet there to the next machine. The next machine is just a regular old rack mount PC. In fact, it's a Dell R720. Nothing exotic about that at all, but we went out and bought the biggest, meatiest GPU engine we could find. So this case, it was a Tesla K10 GPU. I don't know what y'all know about GPUs here. I'll give you my version of it. I think everybody here knows about FPGAs. I find that's usually the case among engineers, but a lot of engineers don't know what GPUs are. What is a GPU? Well, formally it's a graphics processing unit, right? Which tells you nothing about what a GPU actually is. What a GPU actually is just a whole bunch of really simple CPUs interconnected, right, with very high memory bandwidth, right? So what a GPU is basically a lot of CPUs with a lot of high bandwidth access to memory, right? So this is what we use for our dedispersion engine. Basically what we do is we take 13-second data blocks coming out of the spectrometer continuously, and then we use the GPU to simultaneously dedisperse for 531 DMs. So it's repeating this dedispersion operation, not repeating it, it's doing it all in parallel. So it does 531 different DM dedispersions simultaneously, and then sees if anything's there. If it finds something, it reports it, and we collect data if it's detected, and so on. So people often ask why GPUs here and not FPGAs, and it's kind of funny because as an engineer, I always find that there is considerable bloviation on this topic, right? So there's lots of analysis why you should use FPGAs versus GPUs, and they usually say things like the number of flops you can get per unit time, or arbitrary metrics on memory bandwidth. For us, it comes down to a very simple thing. I think in most applications, it's a very simple thing. FPGAs are horrible at asynchronous processing. In GPUs, they're very simple to do asynchronous processing. So FPGAs, what you do is, that's what we use for FFTs, that's what we use for FIR filter banks, things which can be utterly synchronous, FPGAs are great. But for dedispersion, when you want to take the same data set and you want to dedisperse it 100 different ways, well, sure, you could do that in FPGA, but you'd spend your time trying to figure out how to synchronize all these operations. See, all the dedispersions don't operate at the same time or the same number of operations. Much easier just to spray all these different operations across a whole bunch of CPUs, let them do their thing, sit back and wait, and then let them report back on their own time. And as long as the slowest one comes back fast enough so you can do this continuously, that's what you want. Right? So GPUs utterly inferior in terms of processing, raw processing power, but exactly what you want for this.
So why 531? Is that how many microcores or whatever you have to do?
No, that's how many. So you have to choose the grid for the DMs that you sample, right? So and it's not a linear grid because it turns out that if you want to get uniform sensitivity, you take small steps at small DMs and then larger steps for larger DMs. And 531 DM steps for this time frequency resolution turns out to be what you want to cover the whole DM range that we think is valid. So that's how it comes up. It's pretty close to the number of cores, though, that we actually use here. That was a coincidence. Of course, this technology changes all the time, but the ideas don't, and this is always true. It seems like spectrometers want to be in FPGAs, Lots of other things like dedispersion wants to be in GPUs, and that's kind of the way we've landed over and over again. Also, I'll mention, because I think some people might be interested in, we don't always want to do just straight up incoherent dedispersion. What we're desperately interested in doing is finding faster ways to do it that take less effort than incoherent dedispersion. One way is a Huff transform. I don't know if any of you know what a Huff transform is, but it comes from image processing. So Huff transform of an image is something which is intended to detect lines or edges in an image, right? So if you take a Huff transform of my view of this room, I would see all the edges of all the tables. It's good at finding lines, edge detection. Well, that's what you're kind of doing in incoherent dedispersions. You're looking for a line, right? The problem is the line is curved, it's not straight, but we can make adjustments for that. But one of the things we're kind of tinkering around with now is trying to adapt the Huff transform as a faster suboptimal way to do this. So it's the usual trade-off. It's suboptimal, so the detection sensitivity isn't as good, but you could do many more things simultaneously with the processing power that you'd win back. So, status of this thing, it's working. Automated real-time detections of crab giant pulses in a year ago now. Wow, a year ago. So this system has been up and running for a year. Problem is, almost as soon as we got it running, we were interrupted by receiver maintenance, which is a kind of a code word for saying the receiver broke. It took them a while to fix it. It's not one of the frontline instruments at Green Bank, so it took a little bit of politicking to get that arranged. Now the schedule is just the refurbished receiver just went back up. Now expecting to complete commissioning and 24/7 operation by the end of this year. I think it's a pretty safe bet. I just checked it last night, as a matter of fact. The receiver looks good, but it's going to take, now what we have to do is go through this long process where we verify the sensitivity of the receiver, we confirm its flux density calibration, so there's a lot of kind of dirty fingernails work from a signal processing perspective that still has to be done before we productively use it. So we're scheduled for a 1-year run. That started in September, so yeah, that'll work out. We're expecting to see a few FRBs. So if you do the math based on what the FRBs we've already seen, we would expect this instrument, which is currently detected none yet, to see one every 2 or 3 months or so. So over a year, we expect to see 6, 7, something like that. And that's a wild guess. It could be an order of magnitude less, in which case we'll be in trouble, or it could be order of magnitude more, in which case we'll be famous. So there's a range of possibilities for this project. But we have some issues here. We have no immunity to paratons. It's just this one dish. If we see something dispersed, we see it dispersed. We know what we were pointing at, but we can't prove that it wasn't a microwave oven or something else. So that's could be a little bit of a problem. But neither could Parks, so we're no worse than anybody else. Very poor localization. This beam is even fatter than the beam at Parks or Arecibo. It's about 1.5 degrees wide at L-band. So localization is not an option here. The best we can hope for is bright FRBs, so we can do the scattering and polarization thing. There's also this problem that, as you might know, Green Bank, NRAO Green Bank is in trouble. They're being defunded. The word escapes me. I'll say defunded. They're in the process of being their financing is being changed from the National Science Foundation. So they might not be a part of NRAO in the future, and that's complicating things. So here's what we want. This is where we're going, is that thing. I've shown you this picture already, and I've shown you how it works. The instrument we're talking about here has a rather cryptic name, LASA-64x10. So there's lots of other numbers possibilities you could stick up there. LASA stands for Large Array of Small Arrays. And it would look something like this. It would be a whole bunch of tiles. These tiles would be 2 meter by 2 meters squared, which have beams which are degrees wide. But what we would do is we'd assemble them into groups of 64 tiles. That's what 64 up there means. And that's equivalent to a 20-meter dish. So now we have arrays of 64 of these tiles, which act like a 20-meter dish. And then we scatter those 64 tile arrays around over kilometers baselines. And that gives us the spatial resolution. So now we have everything just right. We have these fundamental elements that are giving us big fat beams, which give us a high detection rate, and they're spread over a large area so that we also get high spatial resolution. And if you do the math here on this diagram, what happens is we start off at the top at about 2 meters. We go up, that green arrow goes up because we do 16 beams at a time. So these tiles are electronic beamformers. They form 16 beams in the sky all at once. Then we have 64 tiles in the station, so that brings us down to the right, into the box of productive observing, right? And then we're still not happy, so we may build 10 more of these to get the spatial resolution. That brings the arrow to the right smack dab in the middle of the box where we feel like we're productive. So that's 10 stations, a total of 640 of these tiles. The math right now says it's about a $30 million project. By the way, people freak out, I find out right here when you use numbers like that. But this other instrument we've built here at Virginia Tech in collaboration with the University of New Mexico, University Project, that was $15 million. So it's not crazy to think about those numbers. You just have to get enough people excited. That's the skill set, not anything to do with technology. So this is what we actually want to build. So this is what these tiles look like. In the current design, this is what we're proposing to NSF next week, as a matter of fact. 170 centimeters by 170 centimeters. They're dense arrays of coupled dipoles. So you see every one of those plus signs is a cross-polarized dipole. There'd be 512 of those in the whole tile. Each group of 2 is called a stand. Each group of 4 stands is called a quad. What we actually do is digitize quads. We don't digitize individual dipoles. That's to save money. And then there's a digital beamformer at the bottom. So you can imagine this box, this rectangular thing, which is 2 meters, 1.7 meters by 1.7 meters by about 30 meters high, and that's the fundamental unit. We built lots of those, is the game plan. And this is the system that we're proposing. It's got 3 of these tiles. The tiles output beams, 16 beams. We have to use 4 fibers to get 16 beams out. These fibers, if you're Ethernet people, these are 10 base GLR technology. So this is a long-range optical Ethernet technology. Allows you to send 10 gigabit Ethernet over 10 kilometers or so at a time. So 4 fibers per tile. So there's 12 fibers coming in. They hit a switch. We have figured out through LWA and other projects how to use switches as corner turners. What a corner turner is something which takes all the beams from all the different tiles and reorganizes them into intertile beams. So just by packet switching, what we can do is cause all the packets associated with beam 1 across all the tiles to end up on one fiber coming out of the switch. And similarly, all the packets associated with beam 2 on all the tiles end up on a second Ethernet output going to a different CPU. So that's the fundamentals of the architecture. Then everything else is just an extension of GBTrans. Looks a little bit different in this diagram, but the idea is basically the same. FPGAs to do spectrometry, GPUs to do the dispersion search, and then we just grab everything that looks like a detection. I won't go through this in detail, but this is what the tile electronics would look like. Basically a single conversion from RF to 187.5 megahertz IF. You sample 250 megasamples per second, you stuff it in FPGAs, you do a delay and sum operation to form beams across the FPGAs. The reason we like this architecture is because it's exactly what we use for LWA. And that NSF, helpful tip here, NSF loves it when you say you're just using something that you already worked out on a previous instrument, especially if you were the one who worked it out. So this turns out to be an easy and tractable way to do this. LASA 3 is not LASA 64 by 10, so it doesn't perform as well. That's where we end up there. But it turns out, it's not crazy. I mean, LASA 3 is up there. Parks is Arecibo is a similar distance, just on the opposite side of that box. So it's we'd still expect to see a few FRBs a year if we run it continuously. But it turns out it's useful for other things. I won't tell you what they are. I'll just mention them. Spin down monitoring is a pulsar problem. GP survey is surveying for pulsar giant pulses, which is something that this instrument would be fantastically good for, even this very small instrument. So, wrapping up, FRBs are these things, very mysterious, probably extragalactic, quite interesting no matter what they are. They're plentiful and bright, hard to detect, hard to localize, so that's what the problem is. There's systems going up now everywhere because everybody realizes, I think now that these are probably real. We're probably going to start seeing 10s per year, whereas we've seen 11 to date. We'll probably start seeing quite a few per year. Our system, we'd expect to provide about 6 per year if everything works, so cross your fingers on that. Localization, though, is still hopeless. For localization, LASA is the way to go. And the reason is, again, because it gives us the big field of view, because we're using tiles, and the tiles are spread out, which gives us interferometric localization. I promised to say something about interference. I'll say that very briefly. we're looking at hundreds of megahertz of bandwidth at L-band, which is about where radars start to peter out, about 1,300 megahertz or so, but all the way through GPS, Iridium, Inmarsat, all the favorite acronyms are in there. We contend with all of those, and we do that by a whole bunch of ways. One is we identify bad frequencies, which are just continuously useless. Fortunately, that's a relatively small fraction. We edit out 5% of the frequencies or so. We're golden most of the time. We don't look at low dispersion measures. Turns out that most communication signals, even though you think of them as being kind of continuous in time and frequency, when we see them, if we see them, they're usually reflected off of aircraft or something like that. They look like low DMs. So it turns out we can do pretty good just by, is that a time warning?
Yeah, I think that means there's 10 minutes.
Oh, good. I'm perfectly on time now. Great. So don't look at low DMs. Dedispersion strongly suppresses undispersed signals. This is the other thing. We're looking at very high DMs, so it turns out anything that is not similarly highly dispersed tends to get mushed down into noise. Every once in a while, the matched filter dedispersion process here is saturated. So sometimes you just get signals so big, it just produces a big output in this big detection metric, right? Matched filter 101, right? If you push too big a signal through a matched filter, you get a detection no matter what, right? So in that case, what we do is the process of searching through DMs actually is what saves us. Because as we search through all the DMs, if it's real, what we'll see is a big peak at the true DM and low values everywhere else. Whereas if we're just overwhelming the matched filter, we see just garbage across the DM space. So that turns out just to be a very simple detection to verify that it's peaked. The principal difficulty posed by RFI in practice is not the one most people expect to see. It's labor intensive. So what happens is we keep generating these false alarms. So right now, the sensitivity, if we achieve the maximum, implement this at the maximum sensitivity we could in terms of signal processing, we would get 10 false detections an hour. And that doesn't sound like much, but after 24 hours, you've got 240 or whatever, false detections. That means a graduate student or somebody has to look at 240 data sets and decide which one of those are real, which ones aren't. It's just not practical. So ironically, we have to turn down the sensitivity so the detection rate, the false alarm rate goes down, which is a huge shame. So the way RFI really clobbers this project is not because it overwrites science, it's just because it becomes too expensive to sort through all the false alarms. So this is actually a research opportunity there, not that I proposed it yet, but it's something I keep thinking about. And then finally, I'll say aspects of this project are suitable for students at all levels. We are currently, right now, looking for undergrads to contribute to GBTrans. It's an NSF-funded project where we promised NSF that undergrads would be involved. So I just thought I'd point that out, and you're welcome to see me if interested. Thank you for your time.
All right, let's thank you. So any questions?
At the very beginning, when you were talking about pulsars, you mentioned that we don't see the pulsar if we're not in this cone.
That's right.
Does that mean that we can't detect those pulsars at all?
There are, the number of pulsars we know about are a tiny fraction of the ones that we know are out there. I'll double down on that. Pulsars are simply neutron stars that we can detect through this mechanism. There are many more kinds of neutron stars that don't exhibit this kind of mechanism. There are pulsars that turn on and turn off for reasons we can't figure out. One of the cool things about pulsars is we know nothing about them. And the only way to figure out more is to look for more of them. That's why engineers get involved in this, because you need to build them. It's not like optical observing, where you make images and you infer things from the spectra of the images. Here, it's all about building instruments that can do these kinds of things, that collect enough data to give you, input to allow you to make conclusions about things, where right now you're just running with inadequate data. It's the biggest problem.
There's one point at the presentation when you talked about this wireless junk, this stuff, this terrestrial wireless junk.
Mm-hmm.
And so for radio astronomy, what are some of the challenges that you see when it comes down to, for example, how RF quiet does it need to be at the dish for you to do these types of observations?
So ironically, it's not, I'm probably a bit of a heretic by saying this, but I live in both worlds, so I feel like I could say this. It's not as much about quiet zones or having a level of RF quiet. The bigger problem, the far bigger problem, is the fact that all modern science, radio astronomy, is not in narrow bands, but it's huge bands. I mean, everything I do is over hundreds of megahertz of bandwidth, right? We get away with it here only because comm people haven't figured out how to stuff that spectrum with signals yet, right? So the real contention, is not about levels. It's about how to do some kind of time frequency multiplexing so that when engineers figure out how to stuff the spectrum, we can still use those kinds of bandwidths. You think it's bad here. Below 100, below 1 gigahertz, it's even worse. So LWA, for example, works from 30 to 90 megahertz. You know all the stuff that's there. The only reason we survive, again, is not because signals are weak. They certainly aren't. We have all kinds of stuff that we see all the time. The reason we survive is because we figured out how to carve out the worst of it, so the rest of it we can work with. So the big problem in the future from a spectrum management perspective is that, figure out how to time frequency multiplex with everything, which I think astronomers are more than willing to figure out how to do. But right now there's all this kind of weirdness, because people like to be in fixed allocations. And astronomers have their little allocations, which are useless for most modern science, but they're important because they're kind of a foothold on the spectrum. It's a very complicated issue.
So you gave this example where there were around 250 false detections per day, and you said that you'll have to then manually look at those.
Yeah.
So how do you do that? Once it's detected, how do you tell whether it's a legitimate detection or whether it's a false alarm?
So there's a whole bunch of metrics that get spit out every time we do a detection, but we're always looking at things like this, for example, right? So it's like medical imaging. Right, experienced doctor, can look at a mammogram or whatever, and right away see that's cancer, right? An inexperienced person, layperson, looks at a mammogram, says, it's blobology, right? So the trick here is that when you do this enough, you start to recognize, well, that's a nice, clean, dispersed pulse. You're used to the way it's presented. You can see that it kind of has this nice structure to it. If you see other things that they're interference, and you're familiar with that kind of interference, right? So it's blobology, right? And then if you think that you've survived all those tests, then what we have to do is go back and do more sophisticated processing on it. So we always save the raw data, and then we reprocess it to try to get rid of that stuff. But, it's very analogous to medical imaging, I would say.
So is it then correct to say that there is some sufficient statistic for this type of detection, and maybe we don't know what that is? And that's what you are referring to.
Yeah, I think it's a fair statement. You could, in principle, come up with enough numbers to describe the quality of the detection so that you could automate that process and avoid the problem I described. But two problems there. One is I'm not sure how you do that. It's not obvious. The other reason is nobody's working on it because it's labor intensive. Right? Everybody wants, this small group of people, small amounts of money. You have to go where you get the biggest bang. Right now, there's lots you can do before you do any of that. But clearly, if we want to be productive doing this, we have to